Welcome everyone. I'm Henning Schulze, a recent graduate of the Karlsruhe Institute of Technology, and today I will be talking about text-to-image generation with combined generative adversarial networks. So first, what is the problem at hand? We want to generate photorealistic images from natural language descriptions. To that end, we employ a stacked GAN architecture like many of the previous work before us do, meaning we generate our images in a coarse-to-fine fashion using multiple GANs. So a first generator draws an initial image, whereas the following generators then increase the resolution and correct early defects. All of these GANs are trained synchronously. Within that framework, we employ three attention models. The first of which is Xu et al.'s word attention, and this word attention tells the generators which regions of the image are important based on the words of the input. The second attention model we employ is Palmer et al.'s local self-attention, where each pixel value is aggregated with a convex convolution of value vectors with mixing weights, allowing us to model long-range dependencies. The third and most important attention model that we utilize is Hugh et al.'s squeeze-and-excitation attention, which aims to capture channel-wise dependencies. Because the problem or the issue of regular convolutions is that they only consider the local neighborhood and thereby neglect channel dependencies. So first we perform a regular convolution, then follows a squeeze operation, which is global mean pooling and reduces each feature layer to a single value. Then follows the excitation operation, which is a simple ReLU activation function with a bottleneck layer. And from that, we obtain adaptive weights, which are then multiplied back to our feature layers, performing an adaptive recalibration and specifically allow us to model nonlinear interaction among channels. So to quickly summarize our contributions, we've incorporated multiple attention models. We then stabilize the training with spectral normalisation from Yato et al. And lastly, we will demonstrate that improvements on single evaluation metrics have to be viewed carefully. The two datasets that we used are common within the field of text-image generation. They are the CUP dataset, which consists of 12,000 images of birds, and the much more complex and difficult COCO dataset, which consists of about 120,000 images of day scenes, so fruit, several kinds of animals, peoples, buildings, traffic lights, everything. So it's much harder to learn. The two evaluation metrics that we use are the standard within the field of text-to-image generation and are the inception score and the Frichet inception distance. However, before we continue, I would like to point out an issue of the FID score, or rather of how it's used. Because here we can see several papers and they all use the ATN as a baseline. However, all of these three papers here report a vastly different FID scores for the ATN, making their reported FID scores basically incomparable. So to avoid that pitfall, we reevaluate the FID of the other models where applicable. Now we can compare ourselves to the state of the art. So up here we have the CUP dataset, the COCO dataset, the ES and FID. Then we first have the real data, then the state of the art over the past few years, and lastly our two models down here. So let's start with our first model, employing squeeze-and-excitation and word attention. As we can see, it performs fairly well. We score the third highest ES on the CUP dataset and the best FID, though this column is scantily filled because of the issue I've mentioned earlier. On the COCO dataset, we have a similar picture, scoring again the third highest ES and the best FID. The behavior of our second network is also very interesting. Our second network uses squeeze-and-excitation, word, and on top of that local self-attention. And we can see it scores a better ES on both datasets. However, the FID is both times much worse. This behavior is also similar to the CP GAN, which scores by far the highest inception score on the COCO dataset, even much higher than that of the real data, by the way. However, the FID is really bad. And we'll get back to that behavior in a moment when we look at some of the generated images. So here we can see some images generated by our two datasets, by the DMGAN and the ATGAN, and the corresponding real images from the dataset. So let's start with our first model that performed so well on both evaluation metrics. We can see it draws images of high quality, often achieving photorealism. It also managed to draw the most difficult scene, which is that one here, because the description is so rare in the dataset, best drawing a nice coherent shape. Now, I want to get back to our second network that scored such high inception scores, but really poorly on the FID. And we can see it fails to draw realistic looking images. Rather, it draws repetitive features, as we can see here, and that offers a possible explanation for the behavior of the evaluation metrics. Because the FID compares these generated images to the corresponding real images. However, the inception score does not do that. Rather, the inception score only cares about high classifiability and diversity with respect to classes. And these repetitive features, of course, help the classifiability, while they do not harm the diversity with respect to classes because they still correspond to the textual input. So therefore, they managed to score a higher inception score despite a much worse image quality. And that just comes to show that using a single evaluation metric, especially the inception score as a standalone, like some papers unfortunately do, is dangerous and has to be viewed carefully. Now, to conclude, I've also brought some images for the aforementioned much more difficult COCO dataset. As we can see, the difficulty reflects in the generated images, as our and the other models fail to achieve photorealism. Rather, we can see that the networks only manage to grasp concepts. For example, the pattern of a giraffe here, or here we can see the shape of a building and also the resemblance of a clock, which is remarkable and also missing in the other models. So to summarize all of that, we've incorporated multiple attention models into a stacked GAN framework. We achieved a state-of-the-art FID and comparative ES scores. And lastly, we demonstrated that improvements on single evaluation metrics have to be viewed carefully. Thank you for your attention.